go on to section 6.3, and section 6.3 lays the groundwork for 6.4, and 6.4 is the basis of all statistics, at least the ones that we are going to do in this course. So this is going to be full of definitions. So we're going to be looking at sampling distributions of a statistic, and that is the distribution of the value of the statistic when taken from all possible samples of the same size from the same population. And we're going to look at how these statistics estimate the parameter. So what is the sampling distribution of a statistic, such as a sample mean or sample proportion? Well, like I just said, it's the distribution of all values that the statistic can take when all possible samples of the same size are taken from the same population. If you've already done the discussion question for chapter 6, that's what you're doing. You're taking many samples of size 5 from different kind of populations, and you're seeing what happens to them. And we represent them mostly in a probability histogram is where we're really going to go here. So let's first talk about the sampling distribution of the mean. So we take the mean of a sample of a certain size from many as we can from the same population, and then we look at the distribution of that statistic. So here, for example, we're going to take samples of the same size for a random variable, and we're going to find the mean for each sample. Then we record those sample means and we draw a distribution of that, and if our sample size is big enough, these always have a normal distribution. Okay, I might be getting ahead of myself here, but if your population is normal, the distribution of sample means will always be normal. But here's the kicker, and I think we'll talk about this more in the next section. If your sample size is big enough, even for very non-normal distributions, the distribution of the sample means will be normal, and then we can use the strategies that we used in the last section to find probabilities. So sample means target the value of the population mean, and the distribution of sample means tend to be a normal distribution. We can do the same thing with variances, calculating the variance of samples of a certain size and then looking at the distribution of those variances. And this is what that's going to look like. So again, we take a sample of a certain size, we collect many of those, we calculate the variance for each sample, and then we put them in a distribution. Now, the sample variances does have a skewed distribution, but it's still a very good estimator for the population variance. And again, the sample variances target the value of the population variance. This distribution is slightly skewed to the right. The sampling distribution of a proportion, guess what? It's taking samples of a certain size from the same population, calculating the proportion of that sample that has a certain attribute, and then we graph them. And so again, samples of the same size from the population, calculate the sample proportion, take all those sample proportions and put them into a histogram or a distribution, and you can see it's normal. And again, when it's normal, we can use table A2, or we can use the normal distribution calculator in StatCrunch. But here's some things. When we talk about a population proportion, P is the population proportion. Now, I am working as a statistics tutor at another institution, and the book that they use uses pi as the population proportion, which does fit our pattern of parameters have Greek letters and statistics have regular letters. We're going to use P for population proportion, and then this is called P hat that we're going to use for our sample proportion. And again, when we take the sample proportion targets the value of the population proportion. The distribution of the sample proportions tend to be a normal distribution. Now, these are called unbiased estimators. And when we talk about unbiased estimators, what that means is there's no built-in error. They help us make pretty good guesses. So they target the population parameter. So again, because they're unbiased estimators, these statistics are better in estimating the population parameter, and that's what the science of statistics is, using sample data to estimate population data. Now, medians, ranges, and standard deviations are biased estimators. So they don't target the population parameter. Now we are going to talk about standard deviation distributions because the bias is small enough that we can still make some pretty good estimates. So here is how we would do a sampling distribution. Now, this is similar to what you're going to do in the discussion activity using an applet. Okay, so take one die and you're going to roll it 5 times. You want to find the mean of the values, the number of pips that come up in those 5 times. You also want to calculate the variance and the proportion of odd numbers. So what do we know? Well, we know that if we do this 10,000 times, we're going to get a mean of 3.49. And if we take our 10,000 sample means and we put them in a histogram, here we go. Notice that the mean is going to be up here in the top, and it's at about 3.5. So the mean is 3.5. The mean of 10,000 trials is 3.49. If we would go on even more than 10,000 trials, that sample mean would come up to 3.5, and then our distribution is normal, meaning it's bell-shaped, peaked in the middle. We can do the same thing to the sample variances. So if we find the mean of the sample variances, that comes out to be 2.88. Here is our distribution, and notice our population variance is 2.9. And here's our distribution, and if we would do a quick sketch, you can see how it's skewed to the right, but how our mean of 10,000 sample variances is very close to the population variance. And When we're looking at the proportion of odd numbers, we would expect to get, odd numbers half the time. And so our mean of sample proportions is a very good estimate of our population proportion. And notice how our distribution is relatively normal, symmetrical, bell-shaped. Now an estimator is just a statistic that we use to estimate a population parameter, and we say we're going to use it to infer. Well, we're doing inferential statistics, so we infer, and infer is just a $5 word that means estimate. An unbiased estimator is one that is equal to the corresponding population parameter. And us unbiased estimators are proportions, means, and the variance. Now, biased estimators do not target the value of the population parameter, the median, the range, and the standard deviation. But as I said before, the standard deviation is going to be close enough, so we might use it. Now, why do we always talk about sampling with replacement? Well, we do that because, and I'm going to go to reason number 2. Sampling with replacement gives us independent events. So that means the probability of our event does not change by what has happened on previous events. When we look at a small sample from a large population, we can say, yes, the probability of our event changed very minutely, but not in a significant way, so we're okay with that. But be careful. These require simple random samples, so we need to be careful of bad sampling, such as voluntary response or convenience samples. So remember, bad sampling technique gives us bad data, which gives us bad conclusions. So no fancy math, no amount of computer calculations and manipulations can give us good conclusions from bad data. We have talked about the sampling distribution of a statistic in general. We have talked about sampling distribution of the mean, which will be normal, and the mean of the sampling distribution is a very good estimator of the population mean. We have looked at the sampling distribution of variance, which the mean of the sampling distribution of variance is a very good estimate of the population variance, and that will give us a skewed to the right distribution. And then we've talked about the sampling distribution of the proportion, which again, the mean of the sampling distribution of the proportion is the proportion of the population, and it is a normal curve. And then we talked about why these are good estimators. Let's do an example. So we're going to go to page 264, number 10. So let's go to page 264 and look at number 10. Now I'm going to say that these are kind of tedious problems, but the idea here is to understand what's going on. So what we're going to do is we are looking at, alright, so our population is 459. Okay, so we're going to find samples of size 2, and they're randomly selected with replacement. So on number 10 it says find the proportion of odd numbers for the population. So we're going to have to come up with our possibilities in our sample space. Find the proportion of odd numbers. So we're looking at samples of size 2, and then in each sample we're looking at the proportion of odd numbers. So let's look at our sample space. I can have 4 and 5. I can have 4 and 9. I can have 5 and 9, and I can have 5 and 4. I can have 9 and 4. I can have 9 and 5. I can have 4 and 4. I can have 5 and 5, and I can have 9 and 9. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 possibilities. Okay? So all my probabilities are going to be over 9. So let's come up with our table, and we want to know the sample proportion. So that's going to be p hat. And I usually use a cursive p so that you can tell that it's a lowercase p. And we want to know the probability. And there's why I use a lowercase p, because the probability. Okay, so the probability that there are no odd numbers. Well, there we go. That's the only one that there's no odd numbers, so our probability is 1/9. The probability that half are odd numbers. Well, there's 1, 2, 3, 4. So that would be 4 out of 9. And the probability that they're all odd numbers, well, that's going to be 1, 2, 3, 4. So there's our probability distribution. Now, it says construct a similar table. We did that. Find the mean of the sampling distribution of the sample of odd numbers. Okay, so what we're going to do is, to find the mean of the sampling distribution, we are going to take our value times our probability. So that's going to be 1/2 times 4/9 plus 1 times 4/9, and we get 4/18 plus 8/18 equals 12/18. And when we reduce that, that becomes 4/6 or 2/3. Part D is based on the preceding. Is it an unbiased estimator of the population proportion, yes or no? So it says yes. The mean of the sampling distribution of the sample proportion of odd numbers is 2/3. It's equal to the value of the population proportion of odd numbers, 2/3. So in other words, if we go up here, what is our, how many odd numbers do we have? Well, we have 2 out of 3 odd numbers. So the sample proportions target the value of the population proportion. So that's what you're going to be doing in my math lab, and I think you can handle it.